Ranking and predicting redox reactions. So in a redox reaction, there's always going to be one species that is gaining electrons and always one that is losing electrons. Reduction is gain, oxidation is loss. If one of the particles is able to pull the electron away from the other, and it may not be just a single particle, but maybe a group of particles that are doing this, but as long as that electron transfer will happen on its own, it will be a spontaneous reaction. Redox reaction predictions can be made from experimentally determined patterns, so we can essentially mix things together and see if electrons are transferred, and then we can determine who is better at pulling electrons away from each other. So remember that the reducing agent causes reduction. That's what the agent means, is that it's causing reduction, which means it is itself giving up electrons, which means it itself is being oxidized. So oxidation is the loss of electrons. If it is being oxidized, it is losing electrons, which means something else is gaining those electrons. And so it is causing the reduction of something else. It's putting its electrons onto something else. When a reducing agent goes through the process, its process that it itself is going through is being oxidized. Oxidation is loss of electrons. It causes something else to gain electrons. And vice versa, an oxidizing agent, something that gets reduced, and we are red, gets reduced. So reduction is the gain of electrons. So if it itself is gaining electrons, that means it must be causing something else to lose electrons. So there's this partnership between the two, and we're going to switch back and forth. We're going to primarily talk about these agents themselves, so oxidizing agents versus reducing agents, and we need to make sure that we're clear as to if they are themselves the agent. The reducing agent gets oxidized, the oxidizing agent gets reduced. So using these redox tables, we're going to start by taking a look at a couple reactions, and seeing what happens in the reaction will tell us who is gaining electrons and who is losing electrons. So it'll tell us essentially who is the stronger oxidizing agent, and the oxidizing agent gets reduced, and then the reducing agent is the one that is getting oxidized. Oxidation is loss of electrons. The oxidizing agent gets reduced, the reducing agent gets oxidized. So strong oxidizing agents, we're going to rank these, and we're going to write out these half reactions. We're going to stick to using strong oxidizing agents, and we're going to put them at the top left. So we're going to build a table, and so we'll have reactions, so something plus something goes to form something, and we're going to put them into a list, and so we'll have a series of reactions. And what we're going to do is we're going to put at the top left our strong oxidizing agent. So our strong oxidizing agent will be at the top left. Remember, oxidizing agents get reduced. Reduction is gain of electrons. So we're actually going to be talking about these things gaining electrons and becoming something else. If we were to reverse those reactions, if we were to imagine them going backwards, we would be looking at them losing their electrons, and that is going to be, if they're losing electrons, that's oxidation. So that means that we're going to be dealing with reducing agents are going to be on the bottom right hand side. By convention, well, we'll see what this looks like. By convention, these are going to be written as half reactions, and we are writing them as reductions. Again, we could have chose to write them as oxidations, but we're going to write them all as reductions. So we're all going to have the reactants on the left, with the electrons on the left being added to whatever it is else that is reacting in that reaction. So they're all half reactions written as reductions. Spontaneity, again, if we want these reactions to happen, we want them to be spontaneous, we don't have to put any work to get them to happen. It's going to have a stronger oxidizing agent reacting with a stronger reducing agent. So we have to have something that is the oxidizing agent. Remember, the oxidizing agent gets reduced. Reduction is the gain of electrons. And so we are having something that is gaining electrons combined with something that is willing to lose electrons. And as long as you have something that is good at gaining electrons with something that is good at losing electrons, you will have a spontaneous reaction. Otherwise, you'd have to put in some work to get it to happen. So on redox table, we're going to put the stronger oxidizing agent up on the top left, and as long as you have something on the top left combined with a stronger reducing agent, which will end up being below to the right, we will have a spontaneous reaction. So let's take a look as an example as to how this could come together. So we're going to rank these redox species. We're going to use these given reactions, and we're going to say, okay, based on who is taking whose electrons, we'll be able to say who's a stronger oxidizing agent. We'll put them up near the top. And again, we're going to write these all as reduction half reactions. So in terms of things, what they would look like if they were gaining electrons. And the strong oxidizing agents will be on the top left, and the strong reducing agents will be on the top right. We're essentially creating a list of reduction half reactions and ranking them according to who's the strongest oxidizing agent at the top left, and we'll end up with the strongest reducing agent at the bottom right. So the first thing we need to do is consider which reactions happen. So here they are, the same reactions. If we look at that first reaction, we can see that we have cobalt as an ion, and it reacts with indium as an atom, solid atom. And this reaction does happen, it does take place. The cobalt ends up as an atom, so it has gained those electrons. And remember, if you're trying to gain electrons, you're talking reduction. So it has acted as an oxidizing agent. It has caused indium to lose its electrons and to become this ion here. And the loss of electrons is oxidation, and therefore indium is acting as the reducing agent. Cobalt is acting as the oxidizing agent. Cobalt is gaining electrons. Reduction is the gain of electrons as cobalt turns into these atoms. So cobalt can take electrons from indium. That's what we know from that first reaction. So the stronger oxidizing agent, the thing that's better at being reduced, the thing that's better at gaining electrons, is cobalt, because we can see cobalt taking electrons from indium and becoming an atom. So we know that cobalt is a stronger oxidizing agent. So when we start ranking these things, we'll make a list, and we want the strong oxidizing agent to be at the top. Cobalt is going to be higher than indium, which will be lower. So we can start building these lists and think of this as a partial redox table, a listing of half reactions written as reductions. And we can see that between cobalt and indium, cobalt's going to be above indium. Now, I put cobalt as an ion just because that's what I have as a reactant on the left-hand side, but I know I'm going to write the whole reaction as a reduction reaction. Just by convention, we're going to write it as a reduction reaction, so the electrons will always be on the left-hand side, and they'll always be gained by it. And so for cobalt, I can show, okay, here's cobalt. It's gained its electrons, and it's become this cobalt atom. Now, indium, though, I have as a metal on the left-hand side and an ion on the right-hand side. But when I go to put it in my redox table, the convention is they all have to be written as reduction reactions. So I have to make sure that I have it becoming an atom starting from an ion. So I'll write that as a reduction reaction. From the next one, so let's look at this copper 2+ and cobalt itself. You put them together, and it turns out that the copper will take the electron, so the copper becomes an atom, and the cobalt that was an atom becomes a positive cation. So the cobalt has lost electrons, and the copper has gained electrons, which means copper is better at gaining electrons than cobalt is. And if it's gaining electrons, we know that a reduction is a gain of electrons, and therefore we're talking about copper being an oxidizing agent. It's gaining electrons, which means it's an oxidizing agent. It's causing oxidation. So it itself has gained the electrons. Copper is a stronger oxidizing agent than cobalt is. So on my chart, I know that copper is going to be higher than cobalt is. So I can add it in, and again, I'm going to complete these in a second, but right now I'm just putting down what I have as the reactant. So copper, I'm going to add with 2 electrons, because I want to write this as a reduction. This is the overall reaction, but I'll fill that in a second. So I know that copper is better at gaining electrons, so it's going to be higher up on this list than cobalt is. I know cobalt's lower. That's what this second reaction is telling me. And from the last one, I see copper and palladium coming up, and palladium in this case is the atom, and copper is the ion. So copper's trying to take electrons from palladium, but no reaction happens, which means it can't do it. Copper can't take electrons from palladium. So that means palladium must be better at gaining electrons than copper is, because when copper tries to take them from palladium, it doesn't happen. So palladium must be better at gaining electrons, which means it's a stronger oxidizing agent, which means it's going to be higher up on our list than copper is. So I can drop palladium in there as well, and I can say, okay, between copper and palladium, copper is going to be lower, palladium is going to be higher in terms of the strongest oxidizing agent is at the top of this list, which is palladium. The next strongest one is copper, and then cobalt, and then down here I would have indium, and I write it as an ion, but I will put those in a second to complete the full reactions. But all of these reactions are going to be written as reduction reactions. All the electrons are going to be on the left-hand side, forming the products on the right-hand side. And I am finding their rankings based on what these reactions up here are telling me as to who's better at gaining electrons from whom. And so I can fill in the table, and you could do this as you go through. Just make sure they are all written as reduction reactions. They're all picking up electrons to form their solid atoms. And this now is my ranking of relative strength. The strongest oxidizing agent is at the top on the left-hand side. And what that means is over here, if I want to talk about the strongest reducing agent, remember, reducing agents cause oxidation. Reducing agents, they are being oxidized. Oxidation is loss of electrons. And so indium is the best at losing electrons. Palladium is the best at gaining electrons. Palladium is the strongest oxidizing agent. Indium is the strongest reducing agent. All right, so what we want to look at now is predicting redox reactions. So we looked at using reactions to rank them. And now if we have that ranking, we can use that ranking to predict which redox reactions are going to be the most likely to occur. And you could go and list all of the ones that are possible in terms of, as long as you have a strong oxidizing agent with a strong reducing agent, you'll get a reaction. We're going to predict the most likely one to occur. So we're going to pick the strongest oxidizing agent and the strongest reducing agent. So the first thing we need to know is we need to know who's present. So we just need to keep track of all the entities based on the situation. And then we're going to use a redox table to find out who is going to act as an oxidizing agent. And remember, oxidizing gets reduced, so the reduction is gain electrons. And who's going to act as a reducing agent, and reducing agents get oxidized. Oxidation is the loss of electrons. And sometimes they work as pairs, and so as we look through our redox table, we're going to look for if they need a partner, do we have that partner? And if so, then we can list it as either the oxidizing agent or the reducing agent. And remember, with these redox tables, the oxidizing agents are who is present on the left-hand side, and then the reducing agents are present on the right-hand side for most redox tables. So we're going to stick with that method. So only use species that are there. If you see something that is not in the situation you're looking at, but is on your redox table, obviously it's not present, so you can't count it as something you have. We then want to make sure, once we've found them, we want to mention who is the strongest oxidizing agent and who is the strongest reducing agent. Those two species will be the most likely to go through the spontaneous reaction or react the most. We're going to write the half reactions for the oxidizing agent, and remember, the oxidizing agent gets reduced, so we can write that as a reduction, which is the same way they're found on the table. But the reducing agent, since reducing agents get oxidized, and a redox table gives us their half reactions not as oxidations but as reductions, we're going to have to flip this equation around, take how it is on the redox table, but flip it around, because by convention, redox tables are always written in reduction reactions, and we do have a reduction reaction, but we also have an oxidation reaction, so we have to flip it for the reducing agent so that it is actually an oxidation reaction. We're going to make sure, as always, the number of electrons between the two half reactions balance. So if one loses 2 electrons and the other half reaction is only gaining 1, we'll have to get that half reaction to occur twice. And then we can add them up, and we have our overall balanced equation of the most likely species to go through a spontaneous reaction. So using a redox table, and you have all sorts of different types of these, they may be more or less inclusive, they may be alphabetically ordered. Again, what we're looking for is we're using the strongest oxidizing agent. We want that to be on the top left, and we want the strongest reducing agent to be on the bottom right. So as you move down the table on the right, you're getting stronger and stronger reducing agents. And as you move up the table on the left, you're getting a stronger and stronger reducing agent. So, sorry, I said reducing agent, oxidizing agent. And so if we look at the very top of the table, the strongest oxidizing agent on this table is fluorine gas. And if we look at the bottom right of the table, the strongest reducing agent is solid lithium metal. And so if you were to create a reaction where lithium as a solid metal combined with fluorine as a gas, you would definitely have a spontaneous reaction. As long as you have a strong reducing agent reacting with a strong oxidizing agent, you will have a reaction. If you, let's say we had, let's go with, I don't know, chromium ion here, and we had a, let's pick hydroxide ion. So if this hydroxide ion tried to react with this chromium ion, that's not going to be a spontaneous reaction because we're getting weaker and weaker as we move up the table here. We're getting weaker and weaker reducing agents. So hydroxide is a relatively weak reducing agent, but again, it is all relative. And we can see that as we move this way, we're getting weaker oxidizing agents. And if the oxidizing agent is below to the left of the reducing agent and the reducing agent is above to the right, that is going to be a non-spontaneous reaction. It will not occur. But the opposite is also true as well. If we have a strong oxidizing agent, so let's imagine oxygen and water, and say they reacted with, can't find it here, let's go chromium-2 ions. Here we have a stronger reducing agent reacting with a stronger oxidizing agent. So the oxidizing agent is above to the left and the reducing agent is below to the right. So that is going to be a spontaneous reaction. As long as the oxidizing agent is higher on the left and the reducing agent is lower on the right, it will be a spontaneous reaction. So essentially, what we're going to be looking for is, do we have our strong oxidizing agents? So we'll go through the list. And do we have any strong reducing agents? We'll go through the list of the things we have. And of those that we have, are we going to actually get a reaction? And if so, what is it? So let's say we had aqueous cobalt-2 sulfate is mixed with a basic solution of sodium sulfite. What reaction is most likely to occur? So the first thing is make sure you know what you have. And so writing down the actual species, understanding that if you have an ionic substance that is aqueous, you actually have the ions of it, and you don't have other things. So noting that we have these 6 species, they are the things that could go through our reaction. That's the first step. Next step is basically like a word search where we're going through our redox table and we're trying to find these things and we're trying to label them as whether they're oxidizing agents or reducing agents. So you take your list and you take your redox table and you go through and you find them, and there's our cobalt, and there's our sulfate with our water, and there is our water on its own on the left. So these are all the oxidizing agents that we can see on the left-hand side here, and there's our sodium. So those are all the oxidizing agents that we have present. We can then start looking for our reducing agents. So we also have water. So notice that water is on the, could act as an oxidizing agent here, and it could act as a reducing agent up here. So species can be both reducing agents and oxidizing agents, depending on the situation. We also have our sulfite and hydroxide as a reducing agent, and so these are our possible oxidizing agents and reducing agents. So we should sort of keep track and say, okay, let's label this cobalt could be an oxidizing agent. Sodium is going to be an oxidizing agent. Water can be an oxidizing agent. And I connected these two here to say, okay, well, sulfate can be an oxidizing agent as long as it's with water. So the two of them together can act as an oxidizing agent. And then for reducing agents, we can see that our hydroxide can act as a reducing agent, and our sulfite, when it's with hydroxide, not by itself, but when it's with hydroxide, can also act as an oxidizing agent. Sorry, reducing agent, labeling them as reducing agents there on the right-hand side there. So next is to find out who is the strongest. So again, the strongest oxidizing agents are at the top. So going up, these guys are going to be the stronger, the higher up you go. And the strongest reducing agents, as you move down to the right, this will give you your stronger reducing agents. So of all of the things we have, who's the strongest reducing agent? And if you look at it, you say, oh, but I highlighted this half reaction here. I've got sodium, but we don't actually have solid sodium. We have on the other side as an oxidizing agent, we have the sodium ion. So that's what we have. We do not actually have sodium. If we did have a solid sodium, they would say so in the situation. We don't. We do have, though, a sulfite and a hydroxide ion. So those are the strongest reducing agents that we have. We also have water, but it's way down here on the weak end of the reducing agents. So it's not the strongest one. The oxidizing agents, again, we don't have oxygen and hydrogen, so that's not something we actually have in our situation here, so we don't count that as our strongest oxidizing agent. So we just make our way down the list, getting weaker and weaker and weaker and weaker. And the first thing that we do actually have as our strong oxidizing agent is going to be this cobalt ion. So essentially that cobalt ion and these sulfites and hydroxide ions, we have something that is below to the right, our reducing agent, and we have something that is above to the left, our oxidizing agent. That's going to be the reaction that is going to occur. So then we can note who is going to be the strongest oxidizing agent and who's going to be the strongest. There's our strongest oxidizing agent of everything we have. That's the strongest. And our strongest reducing agent is this sulfite with this hydroxide. They're going to be our strongest reducing agent. They're going to go through our oxidation, and our strongest oxidizing agent is going to go through a reduction reaction. So then we can say, okay, well, what is that reaction? Our reduction reaction is cobalt, and again, it's an oxidizing agent, so it goes through reduction. Reduction is gain of electrons. So there's our cobalt gaining its electrons. That's the reaction it is going to do. Our reducing agent is going to go through an oxidation reaction, and the thing is that the redox tables are written as reduction reactions, but this is going through an oxidation reaction, so we have to reverse the reaction itself. And so we are putting the electrons on the right hand side because in a oxidation reaction they are losing those electrons. It is a reducing agent going through an oxidation reaction, which is the loss of electrons. And so we're going to put the sulfite and the hydroxide on the left hand side because that's them acting as a reducing agent. They are going to get oxidized. They are going to go through a reaction in which electrons are produced. They're losing those electrons. So I've taken the exact reaction off the redox table and I have flipped it and written it down here because redox tables give it as reductions, and it is actually in fact an oxidation because it is a strong reducing agent. Then I just need to add them together, making sure that the electrons gained are equal to the electrons lost, and as long as they are, I can just add them together. If it wasn't equal, I'd have to multiply one of them in order to get them to be equal. But if they're equal, then I can just add them up. And do note that we have to flip our oxidation reaction from what it was given on the redox table, because redox tables give them as reduction reactions. Add them up and we're done. This is going to be the reaction that occurs the most in that we have the strongest oxidizing agent, cobalt, going through a reduction, and then we have the strongest reducing agent, hydroxide and sulfite, going through an oxidation. Add them up and we have our overall reaction. All right, try this one on your own. Again, find all the species that are written here, everything that you actually have in your situation, and make sure that you do actually have it. So, for example, if it says that you have aluminum foil, that means you have aluminum foil. You don't have aluminum ions. So be careful in terms of what you actually have. If it says we have copper 1 ions, we don't have solid copper. We have copper 1 ions. So you have to make sure you're careful with what you actually have, and that is the things that you're finding on the table. So if you go through, you say, okay, based on the situation, these are the species I have. I then need to find them on my redox table, my search and find component of it, and decide whether they are oxidizing agents or reducing agents. And if we're just looking for the most likely reaction to happen, we really could stop as soon as we find the strongest oxidizing agent and the strongest reducing agent. But those are all the oxidizing agents that we'd find on the left-hand side of the reaction that are going to be gaining electrons. These are all the reducing agents we'd find on the right-hand side of the reaction, and then it's just a matter of who's the strongest. Which is the strongest oxidizing agent would be the one the highest up on the left, and the lowest one down on the right would be the strongest reducing agent. And so pick them out and then write their half reactions. We're going to write our copper, which is also a reducing agent, but it is our strongest oxidizing agent. You'll find it on both sides of that redox table. And our aluminum, which is our strongest reducing agent. Let's actually make this red. Strongest oxidizing agent is copper. And so it is going to be our oxidizing agent going through a reduction reaction, because remember, oxidizing agents get reduced. Reduction is gain of electrons. And our strongest reducing agent will be oxidized, which is the loss of electrons, which means we have to take its half reaction from the table and flip it when we write it. So we end up with our copper. We just take that exactly from the table, and our aluminum, which we have flipped from the table because the redox tables give them as reductions. And notice that we are producing 3 electrons, and so we're going to have to take this copper half reaction, which only consumes 1 electron, and we're going to have to multiply it by 3. Then we can add them together. Again, note that we have flipped our aluminum reaction based on what the table has given us, and add them up. We have our overall reaction of the most likely reaction to occur based on everything that is going on in that situation.